That's one small step for man, one giant leap for mankind.
When it comes to science, mathematics, and technology, NASA is on the cutting edge. So today, the NASA Teaching from Space program presents a live electronic field trip for teachers and students, which shows just what some of that cutting-edge research is all about. Today's program, The Whole World in Your Hands. And now, live from the Global Hydrology and Climate Center in Huntsville, Alabama, NASA anchor Camille Moody Jennings.
Hello everyone, and welcome to another exciting NASA electronic field trip. Today's program will explore NASA's contributions to worldwide efforts in understanding global environmental change. It'll also talk about how you can hop onto the internet and use classroom computers to look at real Earth system science data yourselves. Now that data is collected by scientists like the one standing behind me right now. This is Greg Cox, and he is the education coordinator for the Global Hydrology and Climate Center. Welcome, Greg.
Thanks, Camille. Hi, I'd also like to welcome everybody here to the Global Hydrology and Climate Center. You may be wondering what all the noise is behind me. Well, I'm actually standing on the computer room floor of the NASA Marshall Space Flight Center Hydrologic Cycle Data Center. This facility is located within the Global Hydrology and Climate Center and is full of fast computers, data storage devices, and communications equipment. We're going to get a personal tour by the woman who's in charge of this facility a bit later in the show. I'm also joined by a University of Alabama in Huntsville graduate student who's using this facility for some of his research work, and by a teacher and some of her students from a local school here in Huntsville. They're working with researchers here at the Global Hydrology and Climate Center on a project looking at soil moisture, and we'll talk a little bit about that in the show. So, with that, we're looking forward to an exciting show, and I'm going to throw it back to you, Camille. Thanks.
All right, thanks, Greg. We'll be back in just a moment to tell you more, but first, let's meet the other sites joining us for today's program. Lisa?
Hi, I'm Lisa Ostendorf. I work for NASA headquarters in the Office of Mission to Planet Earth, along with Dr. Bob Harris, who is joining us today. Bob is the head of our science division. Bob, can you tell us a little bit about the overall program of Mission to Planet Earth?
Thanks, Lisa. I'd love to do that. We're going to talk about climate change and global hydrology today. Now let's think about news events in the past few years. We've had floods in the Mississippi, we've had storms along the California coast, droughts in Africa. All of these events have had a profound effect on human society with enormous economic cost. NASA's Mission to Planet Earth is a challenging new international effort to put together a global observing system that will help us understand the climate system. Satellites offer a unique perspective whereby we can understand changes in all of the factors that control climate: deforestation, changes in sea surface temperature, and many other environmental variables. Now, I'm sure that the students in our classrooms today will all use data from Mission to Planet Earth in their future careers as foresters, as farmers, and even as lawyers.
I'm sure they will too. Joining us also in our studio today are students and teachers from the Stillwater Schools of Oklahoma, as well as some pre-service teachers from this campus at OSU. Now, I want to remind you that inside your teacher packet of materials, you will find a lot of the activities that we will be conducting live on the show today. I also want to remind you that today's program is interactive. So keep in mind, whenever you have a question, please call us at the number that you see at the bottom of your screen. Now it's time to meet our last and final site for today's program. So let's go live to NASA headquarters in Washington, D.C. Hello, Michael.
Hey Lisa, howdy Camille. I'm Michael Keeler from Hydrologic Corporation. That's Farzad Mahudian. We're teachers at Gonzaga College High School. We work with our students to develop the Earth System Science community curriculum. In our curriculum, students go over the internet to EOS-DIS and get data related to the Earth system to study issues related to global change. We've had tremendous success, largely because of the support of people like Jim Harris. Jim Harris is the program manager for high-performance computing in the Office of Mission to Planet Earth at NASA headquarters. Jim?
Thanks, Mike. We here at NASA are always happy to help education groups like yourselves because we feel that a highly educated, well-informed populace is going to be important to sustaining the health and well-being of the Earth. While NASA is committed to providing global observations to career research scientists, we're also just as committed to providing those same data and the output products from those scientists to the public at large. It is through the advances of computer and communication technologies that we're looking forward to do this, and we certainly are very, very much committed to making this data available to interested students like those participating with us today. And we think that they will be better informed, and when they are called upon in the near future to make decisions about the future of this planet, they'll be able to do that from an informed state rather than one that does not have all of the data necessary. Back to you, Camille.
Thanks so much, Jim. You know, it's clear that learning about planet Earth is everyone's job, and to execute that job effectively, we need to know which Earth systems interact, and we need to know the process by which we can study those systems, as well as the tools required in order to carry out that process. And putting all these elements together will help us address the overriding concern which faces our planet.
The concern: Earth is changing.
From its earliest days, the Earth has experienced changes in land patterns, atmospheric composition, ocean dynamics, and life itself.
To address this concern, we must ask questions and form hypotheses.
What interactions shape these changes? What range of natural variations is possible? How have human activities contributed to worldwide environmental change? What future can we predict for our planetary home?
To answer these questions, we must experiment and collect data.
NASA monitors planet Earth using data from ground studies, aircraft, and satellites. That's because only from the vantage point of space can we get a full picture of how the whole Earth is changing. NASA's Earth Observing System, an array of global observation satellites, will make the first long-term, widespread measurements of the interrelated elements of the Earth environment.
To make our observations meaningful, we must analyze the data and build models.
Global change measurements are combined to build computer models of Earth processes, simulating how the atmosphere, land, and oceans interact as a system. As these models incorporate more and more data, we will better understand our Earth and be more effective in predicting how it will change over time. Building accurate models is a complex task, but through a combination of improved space observations, faster computers, and advanced modeling techniques, global change data can be turned into useful information relevant for businesses, decision makers, farmers, fishermen, and educators.
Which is why we must communicate our findings.
The information developed from Earth observation will help all of us make decisions about our world. To encourage use of transmissions from the Earth observing system, a data and information exchange network is available to scientists and other users around the world. This computer system, called EOS-DIS, enables easy access to data for cooperative use of global climate change research. You, teachers and students, are many of our most important users, and now you can tap into these EOS-DIS data centers to hold the whole world in your hands.
And holding the whole world in your hands, or at least accessing information with a computer keyboard at your fingertips, will be the task that you're charged with at the termination of today's program. Now let's take a look at a graphic that will reiterate the process we'll be following throughout today's show. First of all, given the need to understand an Earth system, we must ask questions about the system and form hypotheses in an attempt to answer those questions. Then we must conduct experiments and collect data from those experiments to provide raw information. Then we must analyze this information and build models to present the data in a meaningful format. And by communicating our findings, we create both a better understanding, but also more questions, and then the cycle ends up repeating again. Now, I want to remind you, we're coming to you live from the Global Hydrology and Climate Center, so the two areas we'll be talking about most today are the hydrologic cycle and the climate system. We do want to remind you, you can ask questions on any area of the environment or Earth observation, but we'd like to encourage you to leave some of those other topics to the end of today's program. Let's get started now by going to Lisa.
Thanks, Camille. Before we start our first activity, it's important to understand some of the basics of the hydrologic cycle. So, Bob, could you give us a short definition?
Sure, I'd be happy to do that, Lisa. As Camille said, sometimes it helps to have the whole world in your hands to talk about the basics of Earth system science. I know many students have heard about the hydrologic cycle, but let's remember the basic elements. First, we have the ocean making up 70% of the Earth's surface. As solar energy comes in through the atmosphere, the blanket of the atmosphere, water evaporates, goes into the atmosphere, forms clouds, hurricanes, ice, snow. Some of it lands on the ocean, some of it falls on the continents. When it falls on the continents, it makes up surface water, groundwater, some of that being used by human society for agriculture and drinking water, the rest running back into the ocean, completing the hydrologic cycle. Now, with those basics, we should try to think of some questions that would lead to hypotheses that we might be able to test with an experiment. So perhaps somebody will have a question that relates to the hydrologic cycle.
How does temperature change evaporation?
Jillian, that's a really good question, because with that question we can then make an experiment where we change the temperature in the hydrologic cycle and see what effect it has. How about another question?
How much water can the atmosphere hold?
Gosh, Caleb, that's another one we can test with a simple experiment. I'll tell you what, let's send it over to Lisa and see if she can show us how we might do such an experiment.
In your materials package, you'll find step-by-step instructions on how to build your own hydrologic system model, as these students did in their classroom today. Let's find out a little bit about what they learned.
We used these materials to create a mini hydrologic cycle in this soda bottle. We saw all the steps of the water all the phases of the water cycle. Heat made the water evaporate it, and the water vapor rose up, where it cooled and condensed. Then it formed water droplets, which fell back down, starting the cycle all over again. This is what happens on the Earth on a much larger scale.
Keep in mind that in your classroom and when you do your own model, you can alter any of the variables that you wish to. And you can practice being scientists, just like those at our Hydrology Climate Center in Huntsville, Alabama. Are you guys still there?
Oh yes, we certainly are, Lisa. In fact, I want to remind the viewers again of what that activity was. We've got a graphic that will remind you of what soda bottle hydrology is, and we'll take a look at that one more time real quickly, along with the objective, because we're going to be talking about hydrology for the next few minutes. The objective on this is to explore hydrology by using a soda bottle to create a model hydrologic cycle. You just saw the setup that Lisa demonstrated right there at OSU, and now joining us here at the center is Dr. Pete Robertson, who's going to talk a little bit more about the kinds of research and experimentation involved in hydrology.
Well, thanks, Camille. You know, we've got a lot of interesting research going on here at the GHCC. Some of our researchers are involved in trying to actually take measurements, much of the satellite data that you see here on the screen, getting that data from the DAC, and trying to learn more about precipitation processes. And as we just saw, that's a key ingredient to starting the hydrologic cycle, especially on Earth. Other researchers here are involved in trying to build models of moisture transport through the atmosphere. And then other researchers are involved in trying to take measurements from new flight systems. And I might add that we have a flight system which is going to be launched probably in the next several days, and we'll be looking at lightning with that. So that's a key ingredient of the hydrologic cycle.
Okay, thanks. Well now, as you heard Pete mention, we're talking about data collection, and that really starts to bring into play the main focus of today's program, which is EOS-DIS. You've heard it briefly described as a computer network which connects users with Earth-observing data. But if you're still kind of confused as to what the acronym itself stands for, well, don't worry. Not too many other folks seem to know what it means either.
EOS-DIS?
I have no idea.
Repeat that again.
EOS? Education on site.
I don't know. Economical.
Educational.
Early.
EOS.
Gosh, I have no idea. I've never even heard of that before.
I have no idea.
I have no idea.
I'm actually not sure.
Not a clue.
I don't have the foggiest notion.
Couldn't tell you.
I don't have any idea.
I have no clue.
Some kind of spaceship?
Well, that's easy. Earth Observing System and Data and Information System.
Aha, well now hopefully at least you know what EOS-DIS stands for, EOS-DIS. But to really appreciate what it means, let's now go to Greg.
Thanks, Camille. Joining me now is the woman who's in charge of the Marshall Space Flight Center Data Archive here in Huntsville. Her name is Kathy LaPinta, and she's going to give us a brief tour of the facility. Kathy?
Thanks, Greg. Before we go on the tour, I want to make sure that you understand some of the primary functions of a DAC. A DAC collects, processes data, archives data, distributes data, and provides user assistance for the use of the data. The EOS-DIS is comprised of 9 data centers, and each of these data centers, which are located across the country, have their own scientific expertise and provide those same functions I just described to you. Okay, let's go on a tour. Located behind me is communications equipment and cables. These communications equipment allow us to be connected to the internet. We use the internet to collect and distribute data. You can use the internet too to access us. One of the examples that you can access us with is our homepage. You can use our homepage to get access to all our data holdings. In our homepage, we have descriptions of all of our data. We also have samples of our data products so that you can look at the data products before you order them to decide whether those are exactly what you want. It has all sorts of other information like frequently asked questions and real-time data, and you can also order data from us. We have an email area that you can do that. Anyway, this computer here hosts our homepage and other user interfaces. This equipment over here we use to provide data to you. There are various media devices. Examples of the media that we can send you data on are CD-ROMs. They contain about the equivalent of 80 encyclopedias worth of information. We have 4mm DATs, that's digital audio tapes, that hold up to equivalent of 320 encyclopedias. And finally, we have 8mm tape that holds up to 800, equivalent to 800 encyclopedias. Now this computer here is our workhorse, and it provides our archival and processing. And this over here is our archive, and it holds the equivalent of 200,000 encyclopedias. And finally, we provide helpful and knowledgeable staff to help you access the data. And that is a DAC in a nutshell. Now back to you, Camille. Thanks, Kathy. You've got a lot of big equipment back there. And we need to remember that anytime we run an experiment or collect data, that's where it's going to end up being stored. But when we perform those experiments, we need to be concerned with how we make our observations. And that is the focus of the next activity in the print material packet. It's called When You Look, Where You Look. And the objective of this activity is to show how the sampling window affects data collection and analysis. Now, to tell us a little bit more about this activity, we're going to go to the Gonzaga College High School students at NASA headquarters.
When you look, where you look can determine the reliability of your data. Let's roll the tape. Stephen?
When you look, where you look even applies to the flow of traffic through the cafeteria. Here we have 3 times, 8:30, 10:30, and 12:30 on 2 different days. Here we can see our first time, and as you can see, there's considerably little flow of traffic through the cafeteria. Here we have our second time, where you can see there's considerably more traffic through the cafeteria. And soon we'll be having our next time, which you can see has little less flow of traffic through the cafeteria, which is due primarily to the wonderful weather we've been having here in DC lately. Next, we'll go to our second day in the morning at 8:30. And you can see we have a little more traffic flowing through the cafeteria. And then we're going to go again to our second time, which is 10:30. Where you can see there's a little less traffic through the cafeteria than there was before, and that's again due primarily to the wonderful weather we've been having. Now I'm going to turn it over to Harry, where he's going to tell us a little more about how where you look, how it applies to ozone.
When you look, where you look. The Tom's satellite uses a ozone spectrometer, which measures different wavelengths of light. And how could light be measured in the North Pole in the winter? It can't be, because there is no light due to the fact that the North Pole is going through polar night. So it does make a lot of difference as to when you look and where you look.
Back to you.
Thanks, guys. That was good stuff. It was interesting that you brought in the ozone component as well. That's certainly one of the elements we look at when we consider the Earth observing system. Now, whether you're students looking at a cafeteria or whether you're scientists looking at data retrieved on ozone or moisture levels, you need to consider how that data is being obtained and transmitted and received. What happens, for instance, if you obtain data from a satellite that doesn't transmit a clean 100% image? What happens if you have these big dropout patches, these big black gaps? How do you account for information that isn't there? Well, that's the focus of today's math excursion. And to find out more about how we can fill in the gaps, let's go now to Dr. Fritz Hassler at the NASA Goddard Space Flight Center.
Hello, I'm Fritz Hassler at the NASA Goddard Space Flight Center, where I head up the public use of remote sensing data program. We work with all kinds of amazing satellite data, like the eruption of Mount Pinatubo and Hurricane Andrew. On this math excursion, we're going to find out how scientists deal with satellite data, including how they handle gaps in the data and problems with data reception. One problem occurs when the satellite is far away and reception isn't perfect. We can have missing data. Another problem is when the instrument is too close. That's the problem with the SSMI microwave instrument. If we look at this North Pole view, we see that SSMI measures data here and here, but because it's too close, it can't get these little gaps in between. It doesn't observe data here, and we see the gaps all around the Earth. SSMI is designed to measure rainfall by observing ice particles and water droplets in the atmosphere. So any point on the Earth might have 31 observations during the month, but it may only have 29 or 25 because these little gaps move each day. And we have to account for that mathematically in the average. For example, to compute an average daily measurement, add together the daily readings and divide by the number of measurements taken. To estimate the total rainfall for the month, multiply the average daily measurement by the number of days in the month. The execution of this step is essentially filling in the gaps for days in which no data was available. We can look at the data in many different ways. For example, stereographically. Here I am zooming in on the gaps in North America. 3D. Another way of looking at the data is in a time sequence. Here's a movie of total monthly rainfall over the whole globe. Notice the gaps have been removed. I would encourage you students to make your own experiment. Measure daily rainfall on school days for 1 month. Then see if you can use mathematics to remove the gaps and come up with your own estimate of total rainfall for the month.
In our discussions of hydrology so far, we have hypothesized, we've experimented, and collected data. Now let's go to NASA headquarters where they can show us how to model the hydrologic cycle.
In modeling the hydrologic cycle, the first thing that we must realize is that that cycle plays an important feature as a connector between what we would call the Earth's physical climate system and the biogeosphere, or biogeosphere cycle. The hydrologic cycle then is the thing that ties those two together, and now facade, will speak to those.
Thanks, Jim. As a case study of the mediation of the physical climate system and the biogeochemical system by the hydrological system, we're going to look at El Nino. El Nino is an event that takes place every 3 to 7 years in the Pacific Ocean. There's a warming of the ocean, which in turn cuts down on the phytoplankton population, and that in turn affects the food chain as it goes up. What we have on the screen here is a model of the El Nino event. This model is relatively simple. We're only including some of the many factors involved: humidity, wind speed, ocean currents, and so forth, evaporation. Only some of those are included here, but if we scroll down, we can see the interaction of these components will output the effect on sea surface temperature, which you can see is randomly going up and down, but around about a 3 to 7 year cycle is apparent. If we scroll down again, we can see that the model is also confirmed by satellite data of the sea surface temperature. On the lower panel, we have an abnormal warming of the area between South America and Australia. The Peruvian fisheries are strongly affected on the coast there. There's a huge drop in anchovy population, and this has been known long before satellite observation. 12 months later, on the top panel, you see that it's going back to normal. In the winter again, there's that little streak of yellow, which indicates a cooler sea surface temperature. Now back to you.
Thanks, Farzad. Now for some final thoughts on analysis and modeling, let's talk once again with Pete Robertson from the Global Hydrology and Climate Center.
Yes, Camille. One of the things that we're doing here as a project is to try to build the best model of precipitation, of moisture transport through the air, and evaporation from the Earth's surface. One of the ways we go about this is actually trying to take some of the zebra-looking data, the SSMI that you saw Fritz talking about, and try to constrain this model, this mathematical model, as it's evolving in time. And of course, we also want to verify what we're doing with this, and so we're using precipitation estimates taken from the microwave sounding unit, and we're also taking other measurements of cold cloud tops, which is an indirect measurement of precipitation. And we're trying to learn more about our model in terms of the physical processes.
Why do we need more than one set of data?
Well, every satellite sees a special view of the Earth and the various components of the Earth system. This particular microwave sounding unit can give us lots of information about liquid water over the ocean, but nothing in particular over land with this particular algorithm. On the other hand, the cold cloud tops tell us something about the extent of the convection. So we need all of this data.
All right, thanks. I'm sure that there's some additional questions out there, so let's go to Lisa at OSU.
Okay, it's time now for the show to answer some questions. And I think we have a phone call from Corey in New Hampshire. Corey, what's your question?
Yes, I would like to ask, how is the depletion of the ozone layer affecting the hydraulic cycle?
I think that's a great question for Bob.
Ozone is another part of the hydrologic cycle that we haven't talked about. It's an atmospheric gas that affects the radiation coming through the atmosphere and therefore the energy balance at the surface, and determines how much water can evaporate and form clouds, and therefore influences several aspects of the hydrologic cycle.
Okay, I believe we have a question in our studio audience as well.
Is there any chance that we'll run out of fresh water?
Gosh, Melissa, that's a really great question, because, you know, in the world tomorrow we're going to find many more people. We're adding about 250,000 people to the Earth every day, about 93 million new people every year. There are many water shortages around the Earth, so in the future we're going to have to manage our water much, much more carefully. Satellite data will give us the chance to see where the water resources are and be much more efficient in its use.
Camille, back to you.
Thanks, Lisa. And we have a question from one of our students out at the DAC.
This is for the students at headquarters. I was wondering if you can access information from the EOS about deforestation from the internet.
Yes, we can. We can access almost anything from the internet. We can access data from the DAC, from Goddard, from Langley, from even here at headquarters. We can take almost anything over the internet and bring it into our classroom and use it for our science projects, where we use that data to make graphs, to make images, which overall help us with to prove our hypothesis, which we form early on. Now back to you.
Okay, that was a super question, and we're running a little bit short on time, so we're going to have additional opportunities for questions later in the program. I'm going to throw it back to Lisa so that we can start talking about the second phase of our program, which is the climate system. And Lisa will start to address some of the questions and hypotheses associated with climate system. Lisa?
Well, Camille, it's quite clear that a lot of questions have been generated by just talking about the hydrologic cycle. A lot of those have to do with the climate system, which is a great, big, huge question that the mission of Planet Earth is trying to figure out. Bob, can you tell us a little bit about what it is that we really do understand now and some of the things that we are still yet unanswered?
Sure, Lisa, I'd like to do that. I've got the planet back in my hands here to help me out. Let's remember that a major part of the hydrologic cycle is the solar energy that drives the evaporation that makes the water vapor in the clouds. Now, our hydrologic cycle is very influenced by this whole process that we're going through to try to understand how that solar energy budget works. The key that we need to focus on is the greenhouse gases, which determine the energy budget. Recently, in fact, for about the last 10 years, we've had direct observations showing that greenhouse gases are increasing dramatically. CO2 is up 30%. The second most important greenhouse gas, methane, has almost doubled. Now, those are facts. What we don't know is how much climate is going to change and how fast it might change. Those are really the uncertainties that we confront in this area of science. How about some questions on climate change? Has anybody got anything that they want to bring up?
Yes, I was wondering, do we know where these greenhouse gases are coming from?
Well, Melissa, that's really a great question. Greenhouse gases have been studied in some detail. We know that carbon dioxide, which is the most important greenhouse gas of all, comes primarily from burning of coal, oil, natural gas. Methane, the second most important greenhouse gas, comes from things like leaking landfills and natural gas pipelines that have some leaks. So there are a number of different sources that are pretty well understood. But how about any other things that people might have?
Is there anything we can do about this?
Yeah, that's really a great question. There's a lot we can do. First and foremost, energy efficiency. It's the most fastest and efficient way to reduce greenhouse gases in the atmosphere. In the case of methane, we can be more aware of sealing up our landfills, sealing up the leaks in the natural gas pipeline. Well, Camille, there's some real good questions on climate change. Back to you in Alabama.
All right, thank you so much, Bob. You know, in answering those questions that you and your students raised, we've been talking a lot about using satellite data, but really the ultimate verification of any of our observations has to come back to the ground itself, and that is the focus of today's science excursion.
This science excursion challenges you to use images from air, space, and ground-based perspectives to classify land cover types in your watershed. Land cover includes everything from vegetation and bodies of water to buildings and parking lots, and each significantly influences water flow and water quality. For instance, while bare ground or paved surfaces limit water infiltration, vegetation intercepts precipitation, permitting recharge of soil moisture. Mining, road construction, industrial expansion, and the conversion of forests to cropland all decrease the amount of vegetative land cover. Each type of vegetation or material covering the land reflects or emits a particular electromagnetic signature. Earth-observing satellite sensors record this signature as a uniquely colored entity on the satellite image. Within limits, different objects can be distinguished on remotely sensed images by this spectral signature. To a certain degree, it is possible to distinguish different types of land cover, but there are limitations to what can be interpreted from any remotely sensed image. While it's possible to tell a paved lot from an agricultural field, to determine what kind of field it is requires more information than is available in one satellite photo. Try locating your watershed on both a map and satellite image. Outline areas that appear to distinctly indicate different land covers. Then take a field trip to those specific sites. Record the observed cover in each of the outlined areas. Test your accuracy by comparing the predictions of land cover to what is actually there. This process is called ground truthing, and by extending this process, you can use information gained from a small sample of sites to interpret remotely sensed images and make educated guesses as to the extent of similar types of land cover in other locations across the globe.
And hopefully now, too, you have a better understanding of how we can use remotely sensed images to gain a deeper understanding of a watershed or a little bit better perspective. Greg?
Thanks, Camille. As we heard today, obtaining a better understanding of hydrologic processes is vital for improving our models of global circulation and hydrologic cycle. The biosphere and weather patterns are not yet fully understood, but they hold the key to long-term climate change. Once a series of questions and hypotheses have been formed, experimentation and data collection needs to be performed before model building and analysis can take place. These students from Whitesburg Elementary Middle School, along with their teacher and many other schools here in Huntsville, have been working with researchers here at the Global Hydrology and Climate Center to look at soil moisture. These students have been measuring soil moisture using a procedure based on the fact that electrical resistance of soils depends on soil moisture. They've been using a simple digital meter like this and several gypsum blocks or plaster of Paris like this, which are buried at various depths within the ground. Now, soil moisture and water are two fundamental resources of our natural environment. Soil is a layer of porous material between the atmosphere and the geosphere and consists of a complex mixture of mineral and organic solids, water, and air. The water content of soils is of fundamental importance to the many hydrological, biological, and biogeochemical processes. Soil moisture is the water that's held between the surface of the particles and within soil pores. Soil moisture is measured using the devices that I showed you earlier, and it's a very simple process. The students actually hold the meter and measure it at various depths to look at how soil moisture might change at various depths from the surface. Now, most of the students here in Huntsville use good old-fashioned pen and pencil to record their data. But one site here in Huntsville uses an instrument like this. This is actually a mini DAC. It's called a data logger, and it has a maximum storage capability of about 41,000 bytes. The DAC that Kathy told you about earlier here has the capability to store 1.2 terabytes, or 1 million of these floppy disks. So Camille, back to you.
Thanks, Greg. To hear more about analysis and modeling within the climate system, let's go to NASA headquarters.
Thanks, Camille. As we attempt to understand better the Earth's water and energy cycles, two areas are of primary concern. First of all, with clouds, and secondly is that of the radiation and atmospheric circulation. We have Charlie with us today from Gonzaga, who will talk a little bit about the research that he's done on clouds.
An important part of the hydrological cycle is clouds. Clouds affect the Earth's surface temperature in two main ways. They either warm it or they cool it. High clouds warm the surface by re-radiating heat back to the surface from the surface. Low clouds cool the surface by blocking incoming solar radiation. We chose three variables to represent clouds' effects on sea surface temperature. The cloud fraction, or the amount that clouds cover the sky, their altitude, and their optical thickness. As you can see, the clouds, as variables are compared to sea surface temperature, which is the purple black boxes, the effect is not great. This is because it is on the sea, which is a great resistor to heat change because of its great heat capacity. If it were compared to land, the change would be greater. And now back to you, Lisa.
Well, it's obvious that data collection and data analysis and building models is a critical part of the scientific process. But you gotta be careful. As you can tell from our next activity, is it getting hot or not? When you can see that making conclusions off of existing data sets can actually be dangerous. Let me give you an example. Can someone here in the studio audience give me an idea of what they see when they see the measurements of the deviation of global mean temperature over a period of time of 1978 to 1990? What's this telling you?
The graph shows a tendency of increased temperatures, therefore it's getting warmer.
I can see how you might reach that conclusion. Well, what about this time, though? When you look at this graph, what does this one tell you?
The graph shows temperatures going up and down, kind of in a cycle.
Therefore, it's critical to make sure that you analyze your data and critically do it so that you can understand the complexities of actually reaching conclusions and making them too quickly. Now, it's time to actually take some more questions, and we have a phone call from Nathan in Pennsylvania. Go ahead, Nathan.
Why does the methane gas affect the ozone more than the coal burning or the running of cars?
Okay, Bob Harris, can you take that?
I'd love to take that question. I've worked on methane for a lot of my scientific career. Methane is a very powerful greenhouse gas. It absorbs more energy for every molecule of methane in the atmosphere than do the other gases, greenhouse gases that we're interested in, like carbon dioxide. So we really need to concentrate on reducing the most powerful greenhouse gases first.
Great. I think we have another question in our studio.
Yes, can you tell me, when do you think we will know if it will keep getting hotter?
Okay, Bob, that's another one for you.
Okay, well, that's one that's really been debated a lot by scientists. And the best evidence we have to date, looking mainly at temperatures on the ground, is that it'd take at least another decade for us to understand clearly whether we're in a trend of global warming or not.
Excellent. Hey, Camille, it's back to you.
All right, thanks, Lisa. You know, right about now, I bet folks are sitting there thinking, how can I tap into NASA DAC data sets? Well, that's the focus of today's technology excursion as we hear from Sue Sorley, who will explain how to do just that from the NASA Langley Research Center in Hampton, Virginia.
Hi, I'm Susan Sorley. I'm a User Services Specialist with the EOSTIS Langley DAC. A DAC is a Distributed Active Archive Center which archives and distributes NASA science data. There are several DACs and affiliated data centers located across the country, and each one archives and distributes different kinds of Earth observing system data. The Langley DAC focuses on the areas of radiation budget, clouds, aerosols, and tropospheric chemistry. Each DAC has its own computer system with which users can access the DAC through desktop workstations, Macs, or PCs. Let me demonstrate how you can access the Langley DAC online system. We're starting at the Mosaic homepage. The URL is http://eosdis.larc.nasa.gov. As we scroll down through the Mosaic homepage, we'll come to our data accessing portion of the homepage. We can click on this icon here, which will bring up the data ordering system information. We will type in our display name and click on this button, which will bring up our graphical user interface. We also have a character interface for users who don't have X Windows, are working from a PC, or who have network problems. This is our welcome screen. We ask that each of our users type in their first and last name and their phone number. This helps us identify that person in our system. Once you're in, our main window can be used as a jumping off spot for EOS information and data. We will begin with our inventory search window. If you already know what you're looking for, you can click on the Datasets List button, and our list of data sets that we have available from the Langley DAC will be displayed. We will click on one data set. We will now begin our search. Our inventory results window will be displayed, along with each individual granule associated with that data set. Many of our data sets have browse images associated with them. we can click on the Show Browse window and show our browse image. Next, we will add the selection to our list. We do not allow our users to order data without first selecting the media. We'd like to encourage our users to order their data via FTP. Now we are ready to submit our order. You are assigned an order number from which we can track you, and you are sent an email message directly with an account number and password that are good for 7 days. And that's it. If you have any problems, please send us email at larc@eos.nasa.gov.
Okay, now let's go to the phones. We have Brandon from Idaho on the phone. Go ahead, Brandon.
How will global warming affect the Arctic?
Okay, Bob, I believe you can answer that.
Brandon, that's a really good question because the Arctic is a real hard place for us to maintain a weather station since it's such a fierce climate. Both the Arctic and Antarctic are sort of barometers of climate change. And we have satellite data now which allows us to measure the thickness of the ice in the Arctic, the amount of sea ice over time from one year to the next, and even the annual melting that occurs on places like the Greenland ice cap. So satellite data will give us a continuing sense of how climate is changing in the Arctic region.
Okay, our next call is from Deborah in Illinois. Go ahead, Deborah.
How much has overall global temperature increased due to the increase in greenhouse gases?
Let's go to Pete in Alabama for that one.
Well, that's a very difficult question to ask right now because we have a lot of different factors which are increasing or decreasing our temperature record. We have volcanoes which perturb the temperature signal from year to year. We have El Niños which tend to kick up the temperature, or the opposite event when the temperature falls. And so we have a lot of variability. Our measurements right now are really too crude and too short a period of time, actually, to tell us exactly what the rise or perhaps the fall in temperature might be. But we'll be looking, and as Bob said, in maybe another 10 years, we'll know the answer.
Thanks, Pete. Let's go to our studio for our next question.
Are we the only nation worried about global climate change?
Bob, are we?
Well, most of the industrial nations of the world have put a very high priority on understanding climate change. NASA's mission to Planet Earth, for example, is a partnership that involves Japan, Europe, Russia, all contributing to the satellites and to the measurements that will be required to understand climate change.
Okay, we're going to take another question from our studio. Go ahead with your next question.
Do you think we'll ever be able to control the weather?
Well, let's go ahead and go to Pete in Alabama for that one.
Gee, that's a real challenge. You know, controlling the weather really implies that you're going to be controlling the way that the Earth's energy that it receives from the sun is processed. We probably already have some examples of inadvertent climate or weather modification on Earth, perhaps like damming up certain rivers to form lakes, and that modifies the local climate. But changing it on the scale of a nation or perhaps the whole planet is a big challenge, and that's probably too much to ask.
Okay, we have another phone call. Bill from California, go ahead with your question.
Yeah, I'd like to know how Freon affects the ozone layer and what chemical changes take place.
Well, that's right up your alley, Bob.
Well, the ozone issue is really one which we have good evidence. We have had aircraft, ground-based measurements, and satellites which allowed us to really both understand the process of ozone depletion in the Antarctic, where the freons drift up high in the atmosphere and deplete the ozone, and we also understand the spatial extent of it. The Antarctic ozone hole is almost as large in size as the entire U.S. of A, so it's a very large phenomena. It also influences climate because the ozone is an important part of determining the energy budget of the atmosphere. So it's both a problem in terms of depleting the life-saving ozone and also a problem in terms of affecting the Earth's energy budget.
Okay, thanks, Bob. We have another question in our studio audience. Go ahead.
Yes, how do we make our models better to predict climate change in the future?
Well, Jim, that's for you at headquarters.
Well, I think that the modeling process is going to benefit from two things. First of all, we are getting larger and faster computers, and they enable us to look at things with higher resolutions. I think, secondly, we are in the process of producing instruments and producing satellites that will be making long-term measurements. As we enrich our measurement data sets and as we enrich our algorithms, then the models then will benefit from the parameterizations that come out, and hence we will have better models of our Earth system.
Thanks, Jim. We have Ralph from California. Go ahead, Ralph.
Yes, the upper atmospheric research satellite showed that man-made elements were the dominant in attacking the ozone layer. Yet some political commentators take exception to that. What were the results of that upper atmospheric research satellite?
Bob, that's yours.
Well, the upper atmospheric research satellite gave us conclusive results that it was the chlorofluorocarbons and similar compounds that were depleting ozone. After a very detailed discussion with some of the critics, they agreed with those results, and it's been resolved now. The satellite data was accurate, solved the problem, and we've made the right policy decisions.
Excellent, Bob. Let's go back to Camille in Alabama.
Thank you so much, Lisa. You know, today's program has provided you with a lot of information about our Earth and EOS DIS, but we hope that it's also encouraged you to celebrate our planet and life here on this very unique spot in the universe. To do just that, we'd like to share with you the following music video.
The sun is high, the dust is running on the land. Give us now our daily bread, the blessed rain that falls. The rivers rise and sing again, the hungry creatures call. The wind is he who knows our names, the rain is she who comes again. The flame is he who licks our heart, dust is she all cracked apart. The moon is he that dies and grows. The sun is she both fierce and slow, with hands to hold and hands of stone, and hearts to give and live alone. Celebrate our home on earth. Celebrate our home on
I know that we've all here had a great time talking about some of the questions that NASA is striving to answer, and we've even come up with a few of our own. So, from all of us here at OSU, see ya!
For Jim Harris, Mission to Planet Earth, Farzad, and the rest of the students from Gonzaga, thank you. Adios, amigos.
Bye.
Ta-ta.
And from us here at the Global Hydrology and Climate Center, let's first hear from Greg Cox and Kathy LaPenta.
Hey, thanks, Camille. We really enjoyed having you all today. Come back and see us at the Global Hydrology and Climate Center anytime. We're looking forward to it.
And please order some data from us.
Great.
Thank you very much.
Thanks. See everybody.
Bye-bye. And Pete, any final thoughts?
Well, we've enjoyed giving you a glimpse of the wealth of data that's accumulating on the hydrologic cycle and this DAC and other DACs. We hope you've used it to learn something about how you can involve it in education and how you can test hypotheses and develop new models. See you later.
That's right. It's accessible to anybody, whether you're a scientist or a middle school student or an undergrad in university. If you have any additional questions or comments based on today's program, please post them at the internet address that you'll see scrolling through the credits at the end. And we want to remind you, the final program in the On the Cutting Edge series will come up live on May 4th. It's called Lasers Learning with Light. We'll see you then. Goodbye.
This has been an Oklahoma State University educational television production.